Hi, we are group B11-2018 and we will be discussing an antenna for our 2FH3 design project. First, we'll start off by addressing what is an antenna. An antenna is a metallic structure that converts electric power into radio electromagnetic waves. It usually operates in conjunction with a radio transmitter or a receiver. Antennas come in all shapes and sizes depending on their purpose and function. They can be, but are not limited to, the following shapes: straight rods, bent or angled rods, rectangular or circular planes, or bowl or dish-shaped structures. What are antennas made of? Generally, they're comprised of multiple conductors that are electronically connected to a transmitter or a receiver. Here are some examples of some metals that are used within antennas today. The electric and magnetic fields produced by these antennas are what help them capture or emit these radio waves. Antennas are found in everyday devices that humans use, including cell phones, such as the one pictured right here. So the antenna for this iPhone 6 is this band along the back of it. Antennas can be classified upon the direction that they propagate or receive their signals over. There are three main types of antennas: omnidirectional, semi-directional, and directional. Omnidirectional antennas propagate their waves uniformly in all directions. Semi-directional antennas operate in a specified direction over a large area. Finally, a directional antenna has a narrow beam that propagates in a highly specified area.
Thanks, Justin. Next, we'll be speaking about some of the examples of the different categories of antenna that we see today, including the halo antenna, the parabola antenna, and the patch antenna. First up is the halo antenna, which is omnidirectional. Two dipoles are created by two rods which create a loop but do not touch each other. The waves propagate in all directions, as seen in the diagram to the right. This antenna operates in the VHF range of frequencies of about 30 to 300 MHz and is mainly used in land-based radio communications. Due to the propagation in all directions, there is significant loss of signal over large distances. Up next is the parabolic antenna, which is semi-directional, also known as the satellite dish or dish antenna. In this antenna, the waves are emitted outward from a diode in a specific direction, but then branch out and receiving signals are reflected from the dish back onto the dipole. It usually operates at 2 to 28 GHz and is commonly used for long-range point-to-point communication, as well as within radar systems, as shown in the bottom right, to detect planes and ships. Finally, we have the patch antenna, which is directional. Also known as the microstrip antenna, as seen previously on the iPhone. It consists of a flat patch of metal mounted on another ground plane sheet, and is commonly used within mobile devices due to its low size and cost, as well as ease of fabrication. The typical frequency range consists in the microwave spectrum, and as seen from the diagram on the right, is directional as most of the waves propagate in a single direction. Next, Rudy will be speaking more on the patch antenna.
Thank you, Damien. Now I'll be explaining the composition of simple patch antennas. Simple patch antennas are made of 4 different compositions: a substrate, a ground plate, a microstrip transmission line, and a microstrip antenna. The ground and microstrip antenna and strip are made of conductive materials. The middle is a dielectric material that is made of materials such as fiberglass. The frequency of operation of the patch antenna is determined by the length L of the microstrip antenna. The center frequency will be approximately given by c, which is the speed of the wave traveling in the conductive medium. And c is 1 over square root of epsilon r mu r. Therefore, substituting c back into the fc, we get an equation of 1 over 2l times square root of epsilon r mu naught. The efficiency and range of the antenna can also be determined this way. The choice of substrate is also important. The bandwidth of the microstrip antenna will increase with the increasing of substrate thickness, h, but with limits. We have to consider temperature, humidity, and other environmental ranges of operation to determine the range of the antenna. On the right, we can see the shape and range of the antenna with respect to different values of phi.
Now we will be showing sample code of a simple patch antenna and explaining the process of how to set up, calculate, and plot patterns of the antenna. First, we need to add the OpenEMS path to MATLAB. This will vary depending on where you save the file. Next, we will need to add the physical constants and antenna parameters. This includes the width and length of the patch as well as the substrate parameters. Now we will be using FDTD, which will be an approximation of Maxwell's equation. OpenEMS has a built-in FDTD function allowing us to enter the parameters, excitation signals, and boundary conditions to solve Maxwell's equation. In this specific example, we use a Gaussian type excitation where we enter the center frequency and cutoff frequency as these parameters, as well as the boundary conditions of the x, the y, and the z axes. To set up the FDTD mesh using a library called CSXCAD, first we need to define the meshes with points and intervals in the x, y, and z direction, using the function smooth mesh lines. Then using define rect grid function, we will be creating a homogeneous mesh in the x, y, and z direction. Next, we need to set up the geometry. Since our example is a simple patch antenna, we will be creating a patch, as well as creating a substrate and ground, where the ground is the same size as the substrate. All of these components will vary depending on what type of antenna you are working with. Now we are setting the feeding port as a lumped port. What this means is we are creating a 3D box which contains a feeding resistance, typically 50 ohms, and a current and voltage probe which allows us to measure the current and voltage across this resistance. Next, we will add a NF2FF box using the create NF2FF box function. This function will create surface dump boxes around the structure. Now all we need to do is create a simulation folder, an OpenEMS compatible file, plot the structure, and run OpenEMS.
Thanks, Jesse. This concludes part 1 of our presentation. For the next part of our design project, we will be focusing on the H-patch antenna design discussed in a journal article retrieved from the Electromagnetic Journal, PIER. Thanks for listening.